We have used the tables now to find properties of saturated mixtures, of superheated vapors, and of subcooled liquids. Let's look more closely at how we can find properties of subcooled liquids. Let's begin by looking at water at 40 degrees C and a pressure of 20 megapascals, which is 200 bar. And let's find the specific volume and plot it on a TV diagram. Now, as always, we begin in the saturation tables, where we could use either the temperature or the pressure table. But I want to find the saturation temperature for 200 bar, so I'm going to look in the pressure table. And I see that the saturation temperature at 200 bar is 365.8 degrees C. Now, our state's temperature is 40 degrees C, which is much less than 365. So I know immediately, without doing any TV plot, that I'm dealing with a subcooled liquid. Well, let's go ahead and plot it on a TV diagram. I'm going to start by putting in a 200 bar pressure line, which is this line right here. And I know it's here because 200 bar is less than the pressure at the critical point, which is 220.9 bar. So I've got this pressure line in. And I know its saturation temperature is 365.8. So I can draw that temperature line in. And the 200 bar line overlaps the 365.8 degrees C under the vapor dome. Now, 40 degrees was the temperature of the state of interest. It's less than 365, so I'm going to draw it down here. And where the 200 bar line crosses the 40 degrees C line, that's where our state exists. So we can see that it's here in the subcooled liquid region. Now I can go to my subcooled table, and there is a subtable here at 200 bar, and I can look at 40 degrees C, and this first column, although I've cut the headings off, shows a value of 0.9992. Well, actually that's the specific volume times 10 to the third. So I have to divide this value by 10 to the third, and I get the specific volume from the compressed liquid table is 0.9992 times 10 to the minus 3 cubic meters per kilogram. Let's look at a different problem to solve this problem a different way. We're going to introduce the incompressible liquid model, and all that says is that for all intents and purposes, liquids are incompressible, or very nearly so. Okay, and so we're going to be able to find property values for subcooled liquids or compressed liquids, whichever you want to call them. We're going to get that value from the saturation table, and most materials do not even offer a compressed liquid table. They have saturation tables and superheat tables. Water does have this have its own compressed liquid table, but we found that there are places where we can't even get on that table. So let's look at this problem. This is one of those values that are not on the compressed liquid table. We have subcooled water at 40 degrees C and 2 megapascals, which is 20 bar. And we find the saturation temperature is 212.4 degrees. Now, our temperature of 40 degrees C is much less than that. So I know I'm dealing with a subcooled liquid. And on a TV diagram, it looks like this. I have a pressure of 20 bar, which is a saturation temperature of 212.4 degrees C. And this state's temperature, 40 degrees C, is below that. So this is where the temperature and pressure lines cross. So we see that this is the state on a TV diagram, and we see that it's a subcooled liquid. So if we go to the compressed liquid table at 20 bar and 40 degrees C, we'll find that the minimum pressure of the compressed liquid table is 25 bar. And 20 bar isn't even on the table. So we cannot find a value for this state in the compressed liquid table. So what we're going to do is we're going to get it from the saturation table using the incompressible liquid model. So what that says is that the specific volume of a subcooled liquid, it's approximately, which is to say very, very nearly, in this case, the specific volume of a saturated liquid at the same temperature. So specific volume of a subcooled liquid is equal to the specific volume of a saturated liquid at the same temperature, in this case 40 degrees C. And from the table, this is the saturation table at 40 degrees C, the specific volume is in this column right here, and I see that it is 1.0078 times 10 to the minus third cubic meters per kilogram. Well, how can this be accurate? If we look at our drawing, our TV diagram, we see that the specific volume out here in this subcooled region is below that of the saturated liquid. Well, that's because these TV diagrams are really not scale drawings at all. They're more like schematics, and they're highly exaggerated just so that we can visualize the situation. And so we show this pressure line as going up to the right and being horizontal under the vapor dome. And we stick the tail of it out here in the subcooled liquid region for visibility. The truth is, because liquids are incompressible, these lines really hug the saturated liquid line. And there's virtually no difference between the saturated liquid line, which is this left side of the vapor dome, and the tail on this pressure curve. And so really the specific volume of the subcooled liquid is right here in this red line. And the specific volume of the saturated liquid is basically right next to it. And they're virtually identical. Let's try one that we can get from both tables. Let's go back to a water state of 200 bar and 40 degrees C. And we want to determine its specific volume using the compressed liquid table. And we want to compare that to what we get by just assuming the incompressible liquid model. Well, from the compressed liquid table at 200 bar and 40 degrees C, we get a specific volume of 0.0009992 cubic meters per kilogram. Now, from the saturated table, I said that the specific volume is very approximately equal to the specific volume of the saturated liquid at the same temperature, which is 40 degrees C. And from the saturation table, I get a value of 0.0010078 cubic meters per kilogram. Well, they don't look quite the same, but if we subtract one from the other to get the difference, and divide by the known value, which is from the compressed liquid table, look at this tiny error. The difference in specific volume is 0.00086 or 0.086%. So the error, even when we have a very high pressure, the error in the specific volume taken from the saturation table is less than 1/10 of 1%. And this pressure is at nearly 3,000 psi. So that shows you how little liquid water can be compressed. The specific volume is virtually identical to that of the saturated liquid.